Hey guys, my name is Tensor. Welcome back to the Introduction to Elixir tutorial series. This video will be part 2 in this series, and today we're going to be talking briefly about modules. We'll also talk about functions. This includes, of course, named functions and anonymous functions, as well as closures. And we'll be talking about higher order types and some of the built-in types that exist inside of Elixir and Erlang. To talk about functions, we need to briefly touch upon modules because functions need to exist inside of a module in Elixir. So I'm going to go ahead and define a module in this file called playground. Now I'm inside of a file called main.ex. That's just a general Elixir file, and in here I can use the def module keyword to define a module. And modules by default start with an uppercase letter, and they tend to use camel case. So if this had two words, say playground list for instance, then I would type it like this. Now a module is just a collection of functions, and it's somewhat like a namespace. It basically allows us to control where our functions are and also control the name of our functions. Because when we create a function inside of a module, the module name gets appended to the function name. Now here's an example of what a module would look like with a function inside of it. This module is called playground and it has exactly one function inside of it. That function is called area, and this area function takes in 2 arguments, and that's called the arty of the function, which is pretty important, and we'll get to that in a moment. Now that we've defined this module, we can go ahead and open up IEX and actually pull the module into IEX using a function called C, which is built into IEX. So we type in C and then we put in a string with the name of the file, and this will compile the code in the file and then bring it into the interactive Elixir shell. So in this case, I'm going to type in C followed by main.ex, and you can see here we get back a list with the name of the modules that get brought in through the file. And now I can go ahead and invoke the function that's inside of the module by calling the module name, then adding a dot, and then calling the area name, followed by the arguments that I want to pass to the function. Now if we want to, we can also nest modules inside of one another. So here we have our playground module, and then we have a circle module inside of it, and inside of that we have an area function again. So even though both of these functions have the same name, they have different arties, so different number of arguments being passed to them, and they're also inside of different modules. And so this is completely legal. Of course, because we've changed the file, I need to go ahead and recompile it and bring it back into IEX. We have our playground module, and now we have a playground.circle module as well. And this is the representation of the embedded circle module. So the circle module is a submodule of playground. And of course, I can access the playground circle area function, and I can also still access our playground area function as well. Alright, so now let's talk about functions. Now I mentioned before, functions must always be a part of a module, and in Elixir, function names follow the same convention as variables. They always start with a lowercase letter or an underscore character, and then they're followed by a combination of alphanumeric characters and underscores. Function names can also end with an exclamation point or a question mark as well. And the general convention is that with the exclamation point, the function could potentially cause an error to the runtime, and then with a question mark, the function will often be returning some kind of Boolean type. Now, of course, you do not need to follow these conventions, but it is recommended to do so because that is just the general way that people have done things inside of Elixir. Now, notice I've defined a function here called area of circle, and of course this doesn't actually calculate the area of a circle. It's actually almost exactly the same as our area function up here. The only difference here is that we're using a single line function macro. So instead of having to write def followed by the function name, followed by parentheses with the arguments that we're passing in, and then followed by this do keyword, and then ending it with an end keyword, we can just say def function name, then the arguments, then comma, then do as an atom, followed by the function body. And this is just a way to clean up a function that is in essence just a single line function like this one is. Now when you define a normal function, you start with this def construct, and then you follow it by the name, the argument list, and then the body of the function itself is enclosed in this do end block. And because we're dealing with a dynamic language, we do not have to specify any type of types for the arguments. Now notice that I didn't refer to def or def module as keywords because they aren't. Instead, they are constructs that are called macros inside of Elixir. Now you don't really need to worry about how this works just yet, but just keep in mind that this is just essentially syntactic sugar over top of a different way of defining functions. Now, if I want to define a function that doesn't take in any arguments, I do not have to put any kind of parentheses after the declaration of the name. Instead, I can just type in def run do and then follow it with the block that I want to execute in the function. Now recall that in Elixir, everything is an expression, which means that everything has a return value. And with functions, what this essentially means is that the last line of the function is what gives the function its return value. So in this case, we're defining an area, and of course, we only have one line in it, so the return value will be a times b. Then for our run function, the return value will be the return value of area, as we invoke it here. If I, for instance, added some stuff to the area function like this, we would still have this as the return value for the area function. So just keep in mind that there is no return keyword inside of Elixir. You're just always returning the last line in your function. Now in Elixir, functions are first-class citizens. This means that you can assign a function to a variable. And when you do assign a function to a variable, this doesn't mean that the variable is calling the function and storing the result. Instead, the function definition itself is assigned to the variable, and then you can call the function from that variable. So for instance, I can take a variable s and set it equal to a lambda function using a macro called fn. And what I do is I say fn followed by x, which is the argument that's being passed in. Then I have an arrow, which then has the function body after it. So x times x is the function body. And then we end the function with an end keyword in this case. So now when I want to invoke this function, I can call s dot followed by parentheses, and then I can put in the argument value, which in this case is just 2. So this variable now contains a function that computes the square of a number, and of course we can then call any number in this function. Now the important thing about this type of function is that it's not actually bound to a global name, and therefore it's called an anonymous function, or as I mentioned before, a lambda. Also notice the list of arguments is not surrounded by parentheses. You could put parentheses here. The parentheses generally are omitted. Now I can also use an anonymous function like this to call other functions. In this case I'm calling ioputs, which is input output dot puts, which prints out the value. So in this case I'm passing in x, and then x is then printed out to the screen. So then I can call x, and then I can say pass in hello, and hello will be then passed to the ioputs function, which will then print this out to the console. Now if I want to shorten this call, because we're literally just calling the ioputs function, I can instead set x equal to ioputs \1. And what this is basically saying is that I want to assign the ioputs function that only has a single argument to the variable x. You see, when I just type in ioputs \2, you can see here that we actually have multiple different puts function inside of the io module. One that has an arity of 1, and then another one that has an arity of 2. This is important because of the way that Elixir uses pattern matching. It's very common in Elixir modules to have multiple functions with the same name, and it's also very common to have multiple functions with different arities as well. And so we can differentiate between these functions by including their arity. Now, the other important thing about this specific way of defining a function and binding it to a variable is this AND sign. The AND sign is what's called the capture operator. The capture operator essentially just captures the IO puts one function and then puts it into the X variable. And now, like before, I can just call x.hello and it will of course print out hello and then give us back an OK atom. Now, because functions can be stored in a variable, they can also be passed as arguments to other functions. And this is often used to allow clients to parameterize generic logic. A good example of this is the enum_each_2 function, which implements a generic iteration. It can iterate over anything that is enumerable, such as a list, and the function enum.each2 takes in two arguments, the enumerable, and then a 1rt function. It iterates through the enumerable, and it calls that function on each element of the enumerable. So, if we go ahead and call enum.each on a list of 1 through 4, and then pass in our x function, we now get back a print statement for each number in the list because our x function is being called on each one individually by the enum_each function. Of course, if I want to, I can pass io.puts1 in here directly using the capture operator, instead of passing in the variable x, and I can also write out my own anonymous function directly inside of enum_each as well. Now, the capture operator just essentially turns the function into a lambda, and then that function can be assigned to a variable. And you can use the capture operator to simplify the actual creation of a function or of a lambda in general. So if I go ahead and create a lambda, which takes in 3 arguments, x, y, and z, and then takes z and y, multiplies them together, and then adds x to that, I can do this with the format that we've shown before, but I can also do it in a simpler way with the capture operator. And so what I've done here is created what is essentially the same function by using the capture operator. And all this really does is it says, all right, capture this anonymous function, and then based on the number that follows the capture, that is the amount of arguments that we're going to pass to this function. So we have capture1 times capture2 plus capture3. And because we have capture3, which is the highest number inside of this anonymous function, that means that this anonymous function takes in 3 arguments. So I can go ahead and call lambda.234, and this will give us back 10. Now, of course, each argument is referred to using the capture, and it essentially is capture n, where n is the nth argument of the function. So you can literally use this to go all the way up to infinity arguments if you wanted to. Now, say we've defined a global variable. In this case, I've defined a variable called outside equal to 10. And then we define a lambda. In this case, it's a lambda that takes no arguments, and it just calls IO puts on the outside variable. This creates what's called a closure. Now, the interesting thing about this is that we've essentially captured the outside variable using this closure. So because we've referenced it inside of this anonymous function, the variable gets frozen in this case. And even if we reassign outside to, say, 200, invoking the closure is still going to give us the value of 10 as outside. So in this case, we still get a printout of 10 followed by the OK atom, even though outside is now equal to 200. So as long as we hold a reference to our closure, the variable outside is also accessible. And this is known as, of course, a closure. And of course, by holding a reference to that closure, you indirectly hold a reference to all variables that are attached to it, even if those variables are from an external scope. The closure always captures a specific memory location, and then rebinding that variable doesn't affect the previously defined closure that references that same symbolic name. Alright, so now let's talk about some of the other built-in types that exist in the Erlang virtual machine, and we'll start with the reference type. The reference type is a unique piece of information in a Beam instance, and it's generated by calling the kernel.makeRef or makeref function. Now, according to the documentation, a reference will reoccur after approximately 2 to the 82nd calls, meaning it's very rare to have the reference repeat itself. So in other words, this reference is always going to be unique so long as this Beam instance is active. But if you restart the Beam instance, the reference will need to be generated again from the beginning. And so its uniqueness is guaranteed only during the lifetime of this Beam instance. These are pretty useful for various niche uses, and I'm not really going to get into those right now. Next, we have what's called a PID, or a process identifier. This is used to identify any Erlang or Elixir process. PIDs are important when you are dealing with concurrent tasks and actors, and you use them generally to be able to talk to the different processes and actors. To demonstrate what a process ID kind of looks like, I've started up the Observer GUI. So you can see here we've got this nice little graph that shows us all of the different processes that are running inside of this IEX instance. So IEX is on this process ID, and then there's another process ID inside of it, followed by all of these process IDs, which are all running at the same time. If we look at the Beam kernel, you can see there are quite a few more process IDs which are running by default. And when we build out an application, we get our own tree like this as well. So while I'm not really going to talk about process IDs right now, we will be talking about them more in the future, so just keep them in the back of your mind. Now finally, we have what are called port identifiers, and these are important when using ports. Now ports are a mechanism which exists inside of Erlang that is used to talk with the outside world. In other words, they're used to do input-output on files or communication with external programs. When I call IO puts, this function actually uses a port to communicate with the Emacs shell that I'm inside of, or with the command prompt that you're inside of if you're running it in a terminal. We may get to ports in a much later tutorial. They're really not that important unless you're actually building items that talk to external programs. Now the Beam also has a number of complex or higher level types. First, we'll look at the range abstraction. So I can go ahead and create a range type by calling a number, then calling 2 periods followed by another number. And what this does is it creates a range between these two numbers. So it's a range from 1 to 100 in this case. And to kind of prove to you that we actually have a range from 1 to 100, I can check to see if 89 is inside of our range variable. Now ranges are enumerable, so functions from the enum module know how to work with them. And as you can see here, we get the predictable answer where we get 1, 2, 3, 4, 5, all the way up to 10, and then we get back an atom of OK. Now under the hood, the range isn't actually a special type. It's internally represented as a map that contains a range of boundaries. In this way, the memory footprint of the range is pretty small. So even a million number range is just a very small map. Now let's talk about keyword lists. Keyword lists are a special type of list where each of the elements are a 2-element tuple, where the first element of the tuple is an atom. And of course, the second element can be any type. So in this case, I've created one where the first element is the atom A, B, or C, and then the second element is just the incrementing number value, so 1, 2, and then 3. Now notice that when I actually evaluate this, we actually get back a more elegant syntax. Elixir allows us to actually define these keyword lists using this syntax, where we have the atoms and then the value. Now these keyword lists are often used for small key value structures, and many useful functions are available in the keyword module to manipulate this type. For instance, we can call keyword.get, and then we can pass in the keyword list and then the key of the value that we want to get back. So I passed in B and we get back 2. And just like maps, we can also use square brackets. One thing to keep in mind about keyword lists is that you are dealing with a list, so any lookup operation in this list is going to use a linear time complexity. Now, keyword lists are most often useful for allowing clients to pass an arbitrary number of optional arguments to a function. An example of this is the IOInspect function. Now, IOInspect is like IOPuts in that it just prints out an argument, but you can also call on IOInspect of RD2. And IOInspect of RD2 allows you to pass in various different atoms, and then these atoms allow the IOInspect function to do different things. So IOInspect has a width atom that it will pattern match on, and then it also has a limit atom that it will pattern match on. Notice how it's printing out it vertically rather than horizontally like this. So we're essentially saying width of 3 characters, but limit it to 1 line. Now keep in mind that we're still actually sending only 2 arguments to the IOInspect function here. We're sending in our list here, and then we're also sending in a keyword list with width 3 and limit 1 inside of it. Now you may wonder if it's better to use maps instead of keywords for optional arguments. Well, there are reasons to use a keyword list instead of a map. The keyword list can contain multiple values of the same key, and they can also control the ordering of the elements in the list, which a map can't do. So that's the main reason why you use it for optional parameters inside of a function. Now let's talk about map sets. Now map sets are essentially just the keys of a hash map. The map set itself isn't enumerable, so we could pass it to any of the functions inside of the enum module. And it also has its own namespace called map set, and that's actually how I created this. So I'm setting keys equal to mapset.new, and then I'm passing in a list of the keys, and that gives us back our map set. And I can check to see if a atom is a member of the keys by calling mapset.member with a question mark. And you can see here when I pass in D, we get back false because it's not inside of our keys structure. If I want to, I can then of course create a new map set and put new values inside of keys. We also have some modules for working with date and time types. We can create a date type by using the date sigil, which is just an NA and a capital D, followed by a pair of square brackets, and then the actual date itself. Now notice I can call date.year to get the year. I can of course call date.day to get the day, and I can then call date.month to get the month as well. We can also create a time type using the time sigil, which is just an NA and a capital T. It's a very similar format to the date as well. And again, we can call time.hour, time.minute, and even time.second, and even time.microsecond. And this will of course give us back all of these different values. We can combine the two in what's called a naive date time type, and this uses a NA and then a capital N. Then we put in the date followed by the time, and for the naive date time we can get the year and we can get the hour as well, so we can get any of the properties that are inside of the date or the time. If we want to, we can also then take this naive date time and convert it into a date time type. And the date time type also includes a time zone. So here you can see we actually get a date time type, which is different from the sigil that we have up here and that we have with the time and the date type. And of course, for this new type, we now have the ability to get back the time zone. So these are very useful when representing timestamps and reasoning about time inside of Elixir. Now finally, let's talk about what are called I/O lists. I/O lists are a special type of list that's useful for incrementally building output that will be forwarded to an I/O device such as a network or a file. Each of the elements in an I/O list must be either an integer of range between 0 and 255, a binary, or another I/O list. In other words, an I/O list is essentially just a very nested structure where each of the elements is a bunch of plain bytes or binaries if it's a sequence of bytes. Here's an example of an IO list, and this actually spells out hello world. Now notice it's very convoluted and sort of messy, but if we call IO puts on this IO list, it will actually organize it into a pretty readable format. And what essentially happens here is that under the hood, the structure gets flattened so that it can then be printed out in a human readable output. And of course, we get the same effect when we send this I/O to a file or a network socket. These are extremely useful when we want to stream a bunch of bytes. And while lists are not usually good in this case, because we're just appending a list to another list, we're actually dealing with a constant time complexity rather than a linear time complexity. Now here's an example of creating an IO list. So first we start by creating an empty list to initialize it. Then down here we're going to add a value to it. So IOList equals IOList comma this with a space. And then IOList equals IOList comma is, IOList comma in, IOList comma IOList. So now we get back this nested structure which just says this is an IO list. And of course if we call IO puts, we get the human readable version of this, which is just this is an IO list. Alright guys, well that's it for this tutorial. I hope you enjoyed it. If you did, feel free to like and subscribe. If you have any questions or comments, feel free to leave them in the box below. And if you disliked this video, then by all means downvote it as much as you like.